I worked on DUNE, the Deep Underground Neutrino Experiment. And the objective of DUNE is to measure the properties of particles called neutrinos. They're elementary particles. They're very common, but they barely interact with normal matter. And so it's difficult to measure them. They do a thing called oscillation, where they change from one type of neutrino to the other. And DUNE wants to investigate this principle. So what they do is they have a neutrino source, a place where they generate a lot of neutrinos at once, and they point them in one direction. Then they measure their initial and final state. So there's a detector near the source of the neutrinos and a detector very far away. In DUNE, this far detector is 1,300 kilometers away. This far detector also needs to be very big because neutrinos are so difficult to intercept. Before they start building this giant detector, they wanted to make a prototype called ProtoDUNE. Now, ProtoDUNE was built at CERN. It's basically a scale model of the fire detector, and it's used to test out the technologies used in the fire detector, but also to do things like calibration and to develop reconstruction algorithms. And I worked on a couple of things. Firstly, I worked on data acquisition. We were trialing a new data acquisition system, which was developed in large part at Nikhef, and it's called Felix, or the front-end link exchange. And the nice thing about Felix is that you don't need specialized hardware. In fact, you only need a single card that you plug into a normal computer, and then you can read out your detector data and process it in off-the-shelf hardware. I worked on translating the detector data in the system, and we also worked on compressing this data. When some particles come into this detector, they create showers, which are like cascades where they create more particles that create more particles still. The second part that I worked on is to distinguish photon showers from electron showers. I've also used these photon showers to reconstruct a very short-lived particle called a neutral pion. Then you can match your reconstructed mass to the known mass. You can calibrate your photon shower energy on this. In my work on the Felix data acquisition of ProtoDUNE, I managed to complete a so-called overlay to translate the detector data that we can use to make events, to make images. And it went well. It is still in use in ProtoDUNE today, and I'm very happy about that. The compression of data was very good as well, but it was very slow. And in fact, it was so slow that it unfortunately did not fit into the online data acquisition chain. So we had to look to hardware compression, which did not compress as well, but it was very fast. For DUNE, of course, this is very important that it works. Especially because in DUNE, Felix was eventually chosen to be the main data acquisition system for the detector. It is now going to be integrated in this massive detector in the future. The photon shower selection is quite difficult, but in the end, there was a very clear distinction visible. And so this forms a good extra handle on recognizing particles within the ProtoDUNE detector, but also in the DUNE detector. Likewise, with the reconstruction of neutral pions, worked quite well. I managed to reconstruct a so-called invariant mass peak. And I've laid out a procedure for calibrating the photon shower energy. I have another handle on this shower energy reconstruction quality. Also, since in the fire detector of DUNE, we want to be able to reconstruct the energy of neutrinos. So in a couple of years, hopefully we will see some nice events come out of this fire detector with all the help from ProtoDUNE.